to start with a quiz that we had, and was it problem number 50? Last time was
recording in progress.
We had exercise number 50, right? So let me do it. Number 50. So it says take a derivative of -9 multiplied by ln of x. So to be able to differentiate this, I have to use a new formula that says that derivative of ln is equal to 1 divided by x. So -9 is going to be with us, it'd be multiplied by derivative of ln, which is 1 over x. Or you can write it as -9 divided by x. I believe that was a quiz from Tuesday. And we utilized a couple of formulas that came from this new chapter. It was also derivative of e to the power, which is the same, e to the power. And of course, we also used our favorite power rule derivative. That's the third formula that we already worked with a lot. So that's power of n minus 1. So with these three properties of derivatives of different functions, you can take any exercise here and do it. Let's say problem number 67. So all you do is just carefully use formulas and of course chain rules. So if we have ln of e to the power of x plus 1, then looks like there'll be two formulas that we need to use when you take that derivative. First of them will be a derivative of ln, which is 1 over this expression in the parentheses. So I just lose that ln and then write that parentheses in denominator. And then we need to times this by a derivative of e to the power of x, which is exactly the same e to the power of x, and plus 1 that disappears as it stays by itself. So the point is to use the chain rule whenever you have a composition of functions. So I can try one more exercise, let's say number 69 here, that says take a derivative of ln of x, which is raised to the power of 4. So when you look at this function, then the outside piece will be 4's power. So I'm going to have to use the power rule first to take derivative, and that will be a 4 on the ground and the power of 3. And the parentheses I don't touch, I just copy it on the first step as usual, because in the next step I'm going to have to take a derivative of that ln, which is in parentheses, and get 1 over x. So I usually recommend you to do a few problems from each section. So let's say if you do 3 exercises like I just did, then should be plenty here. So we can move on and I guess cover one more section today that comes from the same chapter, and that will be our last section here. So I'm not going to do 3.3. We skip it and we do section 3.4 that continues with more formulas, with more derivatives for logarithms as well as for different powers. So actually it's 3.5, sorry. Yeah, these are mathematical models that I guess I'm not going to touch, but move to 3.5 that continue the story of taking derivatives, and they provide us with another few formulas. One of them says that if you take a derivative of some power other than e to the power of x, notice that base e of x derivative is exact same thing, e to the x. So here we're going to have exact same thing, but multiplied by ln of a. In the formula here, they have ln of a in front. I can put ln of a at the end so we can clearly see that it's multiplied. You can always commute. So it turns out this is a little bit more general formula here that actually has e to the power of x as a part of it, because technically you could have said derivative of e to the x is again the same thing, but times ln of number e. But this is equal to 1. So that's why this formula that we saw with e to the power of x appeared first. It looks a little bit nicer, I guess, and that's why they like it. So let me use this new formula to take some derivatives of various exponents that have different than e bases. Let's say, how about problem number 3? It says differentiate or take a derivative of 8 raised to the power of x. So I'm going to look at the new formula and write this as a same 8 to the power of x, but multiplied by ln of a, ln of 8. I say ln of 8 is something I can calculate. I can just place this in a calculator and get some type of a decimal. Yes, but 8 to the power of x you can't put in a calculator because x is variable. So don't bother, just keep it like that. Let us try number 11. That's another chain rule exercise, because when I take 3 to the power of not just a fixed number, but something like x squared plus 1 and find its derivative, then once again I write exactly the same thing, 3 to the power of x squared plus 1. Then I have to multiply by ln of 3. The base is 3, so we go with times ln of 3. And then the power happens to be not just x, but something that we can also differentiate, and we have to. So this be 2x. And the product of these 3 factors is going to be our answer. So it looks like we just get to see more exercises, but the good thing about them is they're all very nice and compact. They're pretty short little problems, so you can definitely do a few in this section if you want to get a extra credit, and that'd be, I guess, a smart idea if you feel like getting some extra credit. So now here comes another formula that will work out problems on the next page. So the other formula deals with logarithm base, not e, but any base derivative. So similarly to the formula that we had with ln, very first one on that side, of the page, we're going to have to put a 1 over x. But it's also going to be multiplied by 1 over ln of a. So it turns out that when I had, right, ln a little bit nicer. When I had the previous formula with a to the power of x, I had to multiply by ln. But with this one, I have to divide by ln. I guess these two formulas are nicely summarized here in the so-called section summary. So basically, that's pretty much all this last section of chapter 3 is talking about. So in chapter 3, we just need this last section, and that'd be good enough. So let us do some problems using this second formula here, the problems that appear on the next page. So exercise like problem number 13 that deals with logarithm base 4 of x. Well, base 4, so we're going to have 1 over x. It's always going to be 1 over x, but multiplied by 1 over ln of 4. So please notice that ln is very popular, that logarithm base e, right? Base e, remember, that's 2 point something, right? 718, dot, dot, dot. So this is a number that you don't want to try to write. You better just call it as letter E for convenience. But since it appears in all of these exercises, then I guess we should have some nice short way to name it, and they call it as E. So how about problem like exercise 17? If these get a little bit more involved. So it's a logarithm. So I forgot to say this is prime. That's derivative. That's important because it's not equal. It's derivative equal. So logarithm base 6 of 5x plus 1. So differentiate that one. And I guess that's what we're doing here in this entire chapter. We keep on differentiating. So first step will be to write it as a 1 over, and that's argument of my function, which is 5x plus 1, this parentheses. Then I also need this ln of 6 present, right? That's our new formula, so that's how it works. I can put parentheses here to make sure we can better see this. And now the chain rule says, Alex, multiply this by derivative of what's in the parentheses, and this is just number 5. So we have the result. So it looks like all these little steps is what we hear about, and they start to compose the longer problems from these exercises. So maybe I need a little bit of a room, maybe here on the other side. And do number 25, that will be a derivative of product of two functions, right? You see that we have two pieces here. One I'm going to call as f, and the other I'm going to call as g. So the function f in exercise number 25 is going to be 6 to the power of x, and function g is another factor here. It's a logarithm of base 7 of x, right? Then we're going to differentiate each piece And then we're going to produce that structure, which is a derivative of that product. Let me first differentiate each piece using the formulas. The one above, right? It's the same 6 to the power of x, which is multiplied by ln of 6. And for the second one, I'm going to have to take the formula on the other side, right? Because it's a logarithm and the base of that logarithm is 7. So it'd be 1 over x. So that argument of the logarithm I put in the denominator, and also ln of that base in denominator, which is ln of 7. So now we are ready to produce f prime times g plus g prime times f, right? Because we actually are dealing with derivative of a product. So the product of functions 6 to the power of x multiplied by the logarithm of base 7 of x. So derivative of this equals to, now I have to put f prime, this 6 to the x times ln of 6 multiplied by g, right? And g is here. It's a logarithm base 7 of x. And then plus, so just carefully put these ingredients in a little by little. So I can put x ln 7 in the denominator. And finally, multiply this by function f, which is 6 to the power of x. So it's kind of messy looking expression that you just write down. There is nothing you can do with it, I guess, but to write it down and, well, maybe look at it and enjoy and well, I guess that's really all we care about. So the problems of this kind, where you have only product of two pieces, you must do using the derivative of product formula. Or if you have a quotient, you have no choice but go with derivative of quotient formula. Let me do one with a quotient, like problem number 29, for example. 29. So yeah, these problems, they have lots of little pieces that you put together, but we just practice basically doing differentiations, and that's about it. That's all we do in these sections in chapter 2, in entire chapter 2. So looks like once again I have two functions that divided by each other. So f over g is how I can think of them, right? So the function f is going to be my numerator. Function g is going to be my denominator. So I'm going to need to follow the rule of derivative of a quotient now. So this will be f prime g minus g prime f. So in a way, the problems are pretty much same. They're just tedious, right? So, well, I guess the more you see them, the more you get used to them. And we're now using this new pair of formulas, and that's all it is. So a to the x, or 7 to the power of x, will have derivative such as a same 7 to the power of x times ln of 7. Now function g is even better. Its derivative is going to be what? 4, right? Because x is giving us 1, and 1 which is added is going to disappear. So it's time to write the derivative of that quotient using the formula down below. So in the formula down below, my denominator must be squared. So I can just copy this and square. And now these little ingredients come into play. F prime. Well, that's 7 to the power of x times ln 7. Then we multiply it by g. And that's my 4x plus 1. So I better use parentheses, right? And then the minus sign comes. The minus sign comes, and we have to take a derivative of function g that happens to be just 4, right? And this is multiplied by function f of x itself, so by 7 raised to the power of x. So here is nothing you can do to cancel, because it's actually a difference in numerator. If you really love to cancel things, then we need to factor, and you factor 7 to the x, you're not going to get that parentheses in numerator. So I guess that's pretty much all it is. So we have done with this section, I guess, lots of little exercises, and what I can do next time is just move to the next chapter that will be dealing with antiderivatives. We did derivatives, and now we're gonna do the backward process, the so-called antiderivatives, and that's exactly what this whole chapter 4 is talking about, anti-differentiation. So let us have a little quiz on this. I hope you're going to feel good about the exercise I will find for you. Maybe I can give you problem number 1. How does that sound? I think it's pretty fair exercise, right? So can you try to do problem number 1 for the quiz? And all you have to do is just use this formula that I already utilized today number of times, a to the power of x, or in your case, you're going to have 7 raised to the power of x. So please try to find a derivative in exercise 1, and then, well, you'll be done. So you can log out and enjoy the rest of the day, as well as have a good weekend. It's Thursday, so I guess we be done for this week.